Okay, chapter 14 is actually kind of one of my favorite topics because it approaches chemistry from a really different perspective. Instead of talking about what sorts of chemical reactions there are, what sorts of products can be made, instead of asking those questions, chapter 14 asks the question of how rapidly does a reaction proceed? How quickly are the reactants consumed and the products produced? And we deal with it very quantitatively, so we don't just say, oh, you know, say gunpowder burns quickly and a log burns slowly, or precipitation reaction happens quickly and say a metamorphic transformation in rocks happens slowly. We can talk about actual mathematical equations to describe these rates. We can make precise mathematical predictions about how long it will take to produce some amount of product or how much reactant will remain after a given amount of time. Anyway, which I think is kind of cool. And we call this hole-filled kinetics. So kinetics is the study of rates of reaction. Okay, so chemical kinetics are controlled by 5 factors. So the first is particle size. Okay, so if you have solid reactants, then the size of your individual reactant particles is going to matter. Primarily because the surface of the particle is the only part that has immediate access to co-reactants in order to undergo the reaction. So you can think of the surface area being the real key factor here. And so if we think about burning wood as an example, you can have a mass of wood that's in a big log, and if you manage to get that log set on fire, it's going to take hours and hours and hours to burn because it's one large particle and the fire has to work its way in from the outside. If you take that same log of wood and put it through a wood chipper and get like a big bag of sawdust or even just wood chips, well, that's going to burn much more rapidly because the fire is only working itself from the outside in on these teeny tiny particles. Okay, so particle size can be really important. If you're a chemical engineer and you're wanting to make 10,000 gallons of some product every day in a giant factory, well, you're definitely going to consider taking your solid reactants and grinding them as finely as you can. Okay, the next is concentration. Okay, so concentration for dissolved reactants, the molar concentration of aqueous reactants is important. Also for gas phase reactants, gases also have a concentration. It's proportional to the pressure, so we'll usually talk in terms of pressure, but it's the same idea. If you have a high pressure gas, that means the particles are packed more tightly. There's going to be more frequent encounters between the particles because of that. And so higher concentrations will lead to higher reaction rates. Low concentrations lead to slow reactions. Okay, temperature is a very important factor. Temperature is going to affect every reaction the same. Low temperatures lead to slower reactions. high temperatures lead to faster reactions. And the little physical chemist on my shoulder is telling me I have to give you the caveat that there are a special class of reactions that will have the exact opposite effect of that. But the overwhelming majority of reactions, and all the ones that we'll investigate here in this class, will increase their reaction rate at higher temperatures and decrease at lower temperatures. There we go, I've satisfied my inner physical chemist. Okay, and then okay, so your textbook calls the next point the nature of the chemical reaction. I want to call it energetics, and these are other factors. We'll get into these, and they make up a part of what we call the Arrhenius equation. That'll get a whole section dedicated to it. But this is like how much energy does it require to activate the reaction, and I'll add a second factor here. Sterics. And sterics is another term that you will learn later. That has to do with how constrained is the range of orientations in a molecular collision that will lead to a reaction. Don't worry too much about this. If this all seems like a jumble of new ideas, we'll give it a whole section later on. And then lastly, the presence of a catalyst. So catalysts are extra ingredients that you can add to a chemical reaction that will speed it up. They aren't really a reactant, they aren't really a product. They kind of occupy this special space. They're called a catalyst, and catalysts will speed up chemical reactions. Sometimes they will dramatically speed up a chemical reaction. There are catalysts actually in use all around us every day. And so we'll talk about them a little bit later in more detail as well. But they're very important to industry and to important chemical reactions that drive our modern world. And so catalysts are a very important way to increase the rate of a chemical reaction. I do have a figure here that explains why the temperature affects chemical reactions rate. So this figure 14.1. And what we see here is a graph of the concentration of the reactant A over time. So you see in both of these cases, we start at 0.05 molar concentration of that reactant. Over time, that concentration goes down as the reaction proceeds. Well, at a lower temperature, you'll notice that concentration drops more slowly. At a higher temperature, it drops more rapidly. And this is what we mean by having different reaction rates. If I were to kind of look at how the concentration changes over a particular interval, say in the first 20 seconds of the reaction, you can see that the concentration change at 20 degrees Celsius is much smaller than the concentration change at 100 degrees Celsius. And so this temperature dependence of the reaction rate, like just about everything else I've brought up so far, is going to get much closer attention later on in this section. So we can represent a reaction rate mathematically. Where the rate is going to equal the change in the concentration of some species. I'll just put A. It doesn't have to be a reactant, it can be a product, over nu A, that's a Greek letter nu, and this is the stoichiometric coefficient for chemical species A. And we'll make one quick note here. This is going to be positive valued for products. And it's going to be negative valued for reactants. And we'll talk about why that is in just a second. Let's just finish up this equation. Then you'll have delta T. So the change in the concentration over the change in time. If you have a reactant, then the concentration is going to be going down. And so this delta A, concentration of A over delta T will be a negative number, but our reaction rates should always be positive. And so for reactants, we'll make sure this coefficient is going to be negative valued to sort of undo that and give us a positive value in the end. For products, let's suppose A is a product. Well, over the course of the reaction, its concentration will go up, and so delta A over delta T will be a positive value already, and so we'll keep this coefficient positive. The reason why we need to have the coefficient at all is, well, let's consider a reaction. I'll go ahead and erase that. Why don't I erase the whole thing? So let's suppose I have a reaction that A plus B goes to C plus 2D. If I were to graph this over time, and I wanted to graph the concentration of C, well then the concentration of C would look something like this. Over time, you'd start with 0 concentration of that product, and it would rise over time, eventually approaching some final value, which means that the reaction has concluded. Well, if I were to graph the concentration of D at the same time, then it would look like this. It would climb twice as rapidly, right? Because you get 2 Ds for every 1 C. You'll end up with twice as much D, and at every point along the way you'll have twice as much D compared to the amount of C. And so depending on what product I'm monitoring and using to calculate my reaction rate, I want to get the same number for the reaction rate. I want it to be consistent. And so if I'm measuring from D, then the rate is going to equal 1/2 the change in the concentration of D over the change in the time. And that 1/2 is going to take care of the fact that D is climbing twice as quickly. And again, this too comes from the stoichiometric coefficient in the balanced chemical equation. Let's consider looking at A. If I were to look at the concentration of A, then it would be more like this. So this is the concentration of A starting at some amount and going down until it eventually reaches 0. And of course the change in concentration of A over time would be negative. So this rate would be negative 1/1. We have a stoichiometric coefficient of 1 here. Change in the concentration of A over the change in time. And let's just finish it off here. The rate here would equal 1/1. Oops. Yeah, that negative for the reactant does not need to be here for the product. And we would have the concentration in C over the change in time. Okay, so that is a good way to mathematically define the reaction rate. Now, we've been using these deltas, the capital uppercase Greek letter delta to represent intervals over which we can measure the change in concentration and the change in time. So let's look at some graphs here. Looking at this graph, if I wanted to figure out the rate of this reaction, well, it goes from A to B, so stoichiometric coefficients are 1 to 1. And just to make life a little bit easy for us, let's look at the interval of the first 20 seconds. So we'll look at how the concentration of B has changed over the first 20 seconds. And let's put numbers in here for our rate. What is the change in the concentration of B? Well, it went from 0 to 0.02 molar. So the change was a positive 0. 0. Sorry, this is kind of ugly. My graphics tablet isn't working very well. So I'm trying to write with my mouse. And even my mouse is being a bit fickle. Okay, 0.02 molar. And what is the change in time? Well, we went from 0 seconds to 20 seconds, and so that is 20, there we are, seconds. 20 seconds. And so let's go ahead and quickly put that number into a calculator. Uh, 0.02 divided by 20, and I'm going to get 0.001. So the rate would be, oh my goodness, 0. This is intolerable. 0.001, and that will have units of molar concentration per second. There we go. Fantastic, I managed it. All right, so that's how it would go for a 1-to-1 stoichiometric ratio, like 1 mole of reactant forms 1 mole of product. Figure 14.3 shows what if I have 2A going to B. Sorry, it looks like this 2 got stranded up on the first line, but that's supposed to be 2A goes to 1B. Well, now we've got the concentration of A dropping twice as rapidly, and so our rate will equal -1/2 delta A over delta T. And then here we'll have something like two different products. So if A goes to B plus 2C, then A will drop at the same rate that B rises, C will rise at double that rate, and these are the different ways of representing the rate that will be consistent regardless of which species you are actually measuring. Now, I want to make 2 more points before we are done. Oops, I'm sorry, I had my calculator covering that the whole time. But I want to make 2 quick points here. These Greek capital letter deltas are sort of meant to be used over an interval. If you remember from your calculus, we can imagine taking ever smaller and smaller intervals of time and smaller intervals of concentration change, and eventually we'll get those deltas turned into infinitesimally small intervals. And so the rate will equal 1 over nu A d concentration of A over dt. So Technically, these formulations here are going to give an average rate over that interval. This formulation here will give you what is called an instantaneous rate. We'll get into how we can begin to use instantaneous rates, why it might be useful to at least consider the abstract idea of an instantaneous rate as we manipulate our equations and things like that. Okay, so how do you actually generate a graph like this? How can we measure the concentration of a reactant over time? Well, there are a number of different ways. One of them is through spectroscopy. So if you have an aqueous reactant or product that absorbs a particular color of light, then you can shine light through your reaction chamber here and measure the amount of light that comes through absorption spectroscopy. And usually spectrometers are very rapid to take their measurements. And so if you've got it connected to a computer, then it can measure the absorbance several times a second. And so even if a reaction takes place, rather quickly over a matter of 10 or 20 seconds, you'll probably be able to get enough data points to really see good changes in the concentration of your colored species. So we can take the amount of light in and the light out and convert that into a value called absorbance. And that's usually done by the spectrometer. It's a logarithmic scale, and so I don't want to get into the math behind that conversion right now. But the absorbance is going to be proportional to the concentration according to what is called Beer's law. Okay. I'm embarrassed at how ugly my writing is. That's okay, I need to just get over it. You're probably already all over it. And I'm the only one fretting here. Beer's law. Okay, so Beer's law says that the absorbance is proportional to the concentration. If I have an absorbance of 0.2 at a concentration of 2 molar, then if I double my concentration to 4 molar, then my absorbance will be 0.4. If I double it yet again to 8 molar, well then my absorbance will be 0.8. And so you can use the absorbance to tell what the concentration is at any particular given point in time. And Beer's law says that the absorbance A is equal to, I'm going to just write this on the chalkboard. Okay, enough of this ridiculousness. There we go. Okay, Beer's law says that the absorbance is equal to alpha LC. This is a coefficient that is unique to each colored solute, and so you'll just look that up or measure it with standard samples or something. It will have units of inverse centimeters, inverse molar concentration. And a higher value for alpha is going to be a darker solution, or a lower value for alpha will be a lighter solution for equal concentrations. Alpha is sometimes called an absorption coefficient, and sometimes it's called an extinction coefficient. This here is the path length, and so if you have the light passing through a wider length, then there's going to be more material to absorb that light. So of course the length is important, but you almost always run these spectroscopy trials in a little glass vessel called a cuvette, and they are manufactured to have a length of exactly 1 centimeter. So that's almost always 1 centimeter. And then finally, this is the concentration. Okay, and of course, A is the absorbance. Not the absorption. Absorption is like the act of absorbing something. Absorbance is the measured value of how much absorption has taken place. Okay, so spectroscopy is only one way to measure the concentration of a reactant in situ, or in other words, in the reaction chamber while it's actually proceeding. Other chemical species can be monitored by an electrochemical potential. So we'll talk about electrochemistry, but basically you can measure the voltage across a chemical probe through time. And again, those measurements are usually very rapid. You can take many measurements a second, and so it's responsive enough to monitor the concentration as a function of time throughout the course of a reaction. Okay, that's it for section 14.1.